Slides are in English. I needed a bombastic title to get the talk accepted at OOP, so a more appropriate title would be How Does Design Work when you do functional programming, which is somewhat different from traditional design techniques in more traditional languages. So just to expand a little bit on what Bene said, so I'm an expert on functional programming, and I've been doing functional programming for probably more than 20 years. I'm CEO of a company in Tübingen that does project development using exclusively functional programming and functional programming languages. We do a lot of different functional languages. We also do training and coaching. If you speak German, then and you Google for funktionale Programmierung, then we're usually right before or after Wikipedia on funktionale Programmierung.de, which is a blog on functional programming. And we also run an excellent developer conference, which will happen again on March 22nd in Berlin. So this is hot off the press. BA, which I can highly recommend. So I think, well, I mean, there's different ways to approach design, but so one way to approach design is to build domain models. And the traditional way to build domain models in object-oriented languages is you draw a diagram of in some sense. So there's all this model-driven design stuff where a model means it's something that it's drawing, right? It's not code, and it's not language that's written down. And so this is very different from the way that we approach design and functional programming. So I'm going to introduce a couple of techniques. So the most immediate technique is, well, you try to create a one-to-one correspondence between your problem domain and your program. So. And that means between the problem domain and your code. And that means there will be a lot of code in the slides to come. And when I did this talk at OOP, I got through about 10 slides when I noticed nobody had seen code in Haskell before, which is a nice functional language, very useful for doing talks because the programs are small enough to fit on slides. So this talk hinges on your ability to understand the code, and that means it hinges on you interrupting me when I haven't explained something adequately. Okay, so please interrupt me as we go. So here's a problem domain that we worked on a couple of years ago, which is on semiconductor manufacturing. And this is a slide that I didn't do ourselves, one of our customers did that. So when a semiconductor gets made, before I got into this project, I thought there's a machine somewhere and somebody goes chunk, and a new semiconductor goes out, they put a piece of silicon and they chunk and another wafer comes out. It does not work like that. Instead, a modern microprocessor, if you will, goes through about 1,000 manufacturing steps that are spread out over several weeks. And of course, a modern semiconductor has many layers, so it goes through the same kinds of machines many times in a given factory. These machines are very, very, very expensive, and that means that a factory can't just buy enough machines and line them up in an assembly line, and also they break down all the time. So that means well, there's various complicated problems that have to do with finding out what is the best machine to put your wafer through next, right, when it comes out of the previous machine. Problem sort of clear? So one central abstraction that you have when you deal with semiconductor manufacturing is it's called a route. And a route is associated with a given wafer, and it just has the sequence of steps that it needs to go through. And I've abstracted over that here in this slide. So this is a bunch of Haskell code, and it says, well, here are 3 operations that might be applied to a wafer. One is called track-in. Track-in means that a wafer gets inserted into a machine. Then there's process, the machine does something, so I've simplified a little bit. And then there's track-out when the wafer gets taken out of the machine, right? And so a route is just a sequence, so that's what that means. It says data operation, it's a new data type, and it says an operation, and you can read that vertical bar as or. So an operation is either a track-in or process or track-out. Okay? So the next line says, well, a route, which just has that sequence of operations, is a list of operations. So these angle brackets, these brackets, they just mean list of, right? So a route is a list of operations, and down there's an equation that has an example for a route, and that route says, well, it's a sequence of 4 steps. First one is track into a machine, then it processes, and processes some more, and then it gets tracked out of the machine. Right? You could write that down as it is in Haskell. So one of the central things that you want to do when you model this is you want to figure out what is the next thing that needs to be done to your wafer. And so you need to find out that first operation. right? And so what we do is we write a function in Haskell, and usually the best way to start writing a function in Haskell is you write down its signature, saying what kind of data goes in and what data goes out. And in this case, the signature says, well, we have a route, we really want to know the first operation that comes out. Okay? And then what you then do is you write a bunch of equations to define what that function does in certain cases, right? Now in this case, remember, a route was a list of operations, and in Haskell and in all functional languages, a list is either the empty list or consists of the element at the front and the rest, okay? So because there's these two kinds of lists, either empty lists or non-empty lists, you write two equations, right? And that's what that says. That's why I see these two purple equal signs there. And the first equation is for the empty list, the empty bracket. Well, I'm going to defer to that. And the other one says, well, if your list, the colon separates the first element of the list from the rest, right? And we're not interested in the rest, we're interested in the first element. And this is what's called pattern matching in Haskell, right? So if your list of operations looks like this, the first operation is called op, and then there's something that comes after that, then the head of that route should be op, right? That first operation. Makes sense so far? You all nod? Okay, okay, so that doesn't work. Okay. You nod?
Yeah.
Okay. Now, if you return to that first equation, well, there's nothing you can write down here, right? It says, well, what do you write down here, right? The list is empty. There is no first operation. So usually what you do when you do that direct modeling is as you write your functional program, you discover things, right? The first thing is that there is not always an initial operation. It might be that your route is exhausted, right? That there's nothing left to do, and that usually means that your wafer is finished. And so that function routehead needs to communicate there is no further step to be done. And if you were writing this in Java, what would you do? Who would return null? I would return null, right? Just return null. So yeah. So anyway, so if you're old enough, you remember that there was a time when there wasn't an optional type in Java, right? So that's a fairly new thing that was added an option in Java 8 a couple years ago. So in Haskell has that built in, but I'm just writing down a definition of another data type called option A. So it says, it has a type parameter. You would call it a generic maybe if you're used to Java, called A. And it says an option A is either there or it's not there. Those are the two options that you see there. And the first one is called some. It says, well, there's some thing, some A there. And the other one says none, no, there's not a thing there. And these things after the double colons, they are the type signatures of the constructors of that option type. So the first signature says, well, given an A, I'll give you an option of A, right? So there needs to be an A. Or the other option says none. Well, that is already option A. There's nothing there. Nothing gets passed in. So that arrow means it's the function arrow, right? To the left of the arrow gets passed in, to the right of the arrow. This right, it gets passed out. Okay, makes sense? Okay. So now we can revise, just driven by the way the programming is shaping up, is we can revise our definition of route head. Before that we had route to operation, and now we say route to option of operation. So there might be an operation or there might not be one. And again, there are two equations, and now we know what we can write down in the first case when we have these brackets, which is we can write none. There's not an operation. In the other one we say there's some operation that comes out, and that's good. So when you have that example route, remember it's a track in, process, process, track out, then route head of R1 is going to return some track in. Okay. So we write a bunch of functions. Here's a slightly more advanced function called route advance that we also need is, well, once we've done that first step, we also want to know what happens after that. What is the route after we've done that first step? Okay. And now with the knowledge that we had before, we know we might not always be able to split up the route because it might be already empty, right? And so this says route advance, we put in a route, there's an option, and these round parentheses and the comma just means a tuple. So we package up two things in one and says, well, if there's something comes out, we're going to have both an operation and a remaining route after that, okay? And then route advance R1 is supposed to return, remember it was track in, process, process, track out. It's supposed to return track in as the first operation, and then a list of all the steps that come after that track in. So the track in has been removed. Okay? So that's pretty easy to do. Again, we write two equations. The first one says none, as before, and with the other one, we just package up rest along with the operation. So you think this is all trivial, but of course it's useful as your model becomes more elaborate. So here's another original slide from one of our customers. They said, well, it's more complicated than that. A route is not just a linear sequence of steps. It might be the case that there are subsequences that have to be finished within a certain amount of time. So because there's chemical processes involved, right? And if your wafer gets moldy or something like that, if you don't, if you're waiting too long, right? And so that means, that might be that. So that's what's called a queue time zone inside that sequence of steps. And it means you need to be careful, because once you enter that queue time zone, you've committed yourself to finishing that part of your route within a certain amount of time. And if not, you have to throw away the wafer, and things get expensive, and management gets involved, and QA processes, and you all know what that feels like. Okay. So you saw a very simple example of just direct modeling. We're going to extend that to this queue time element thing. So before that, we said a route is just a sequence of operations, and now we know a route might either consist of operations, but it also might have a queue time zone inside it. So if you just put that language directly into code, then it might look like this. A route is now not a list of operations, but it's a list of route elements. And here's a definition of that route element data type, and it now has two cases. The first one says route, that's the old operation thing. Route op is the constructor there, right? And the other possibility is that there's a queue time zone. And the queue time zone says, well, we have a duration. We have a list of operations inside the queue time zone, and then comes out a route. Then that also constitutes a route element. So more difficult now. Does that work for everybody? So go shake your head if you don't. Okay, good. There's no shame in, so the OOP people, all these are smart people, they were lost at this point. I was going too fast. So here's an example. Again, so what we now need to do is we need every single thing that's inside a route, we need to put a constructor in front that says whether it's an operation or whether it's a queue time zone. So our first example now says route up, route up, route up, route up, and then inside says track in, process, process, track out. But we can also have a queue time zone here where we say track in, and then maybe these two processing steps need to be finished within whatever, 5 seconds or whatever that is. Okay? So, anyway, so if you look at this, you see that, well, let me backtrack a little bit. Here we said a queue time zone is a list of operations, right? But remember that we already generalized a list of operations that constitute a route to a list of route elements. Okay? So look here. So try to remember that image. See that? So what if we did the same thing here, right? If we said inside a queue time zone cannot just be a list of operations, but there could be a list of route elements, right? That's something that I was thinking at my desk while I was writing this code. And so there was a natural opportunity for generalization, and I called up the customer and I said, during development we had this idea. Is it possible, does it make sense to have a queue time zone inside a queue time zone? Because that's what you can do with this, right? And they said, oh yeah, we've been wanting to do this forever, but our relational database will not support it. So if you just are systematic about your programming, because things are, they fit on slides, and if you're careful, then sometimes what happens is domain knowledge drops out of the sky. Moreover, if you look at this, you say, well, there's two places now where a list of route element occurs, right? So you might as well say, well, I'm just going to, here's an example, but I might just as well replace those, right? And write route here. And that really makes sense, right? There's a route that consists of elements, and then inside the route there can be a queue time zone that can also be a route, and so that makes that thing very clear, okay? So this now constitutes what's called a little data type with combinators, right? That's something that we do often in functional programming, in that we build smaller things, that we build bigger things out of smaller things. And the important thing is that it's the same kind of thing, right? So if you're used to sort of traditional object-oriented models, or especially a relational database model, you're used to a hierarchy, right? You combine two small things with slightly bigger things, and it goes up in a hierarchy, and at some point you're at the top. and you have a module or a package or something like that, and then that's the end, right? In functional programming, we try to always go back to the same place. So in this case, that means I can always build a smaller route into a bigger route that contains that route as part of your queue time zone, right? And that's it's a surprisingly general design principle, right? I mean, it says recursion. You might feel uncomfortable with that, but a lot of problem domains have some kind of recursion in there if you just look for it. And so now you can have nested queue time zones like this, where there's a queue time zone that says, well, the whole thing needs to be finished in 7 seconds, but these 2 particular steps need to be finished in 5 seconds. So, there's that. Now, of course, we need to go and revise our functions, right? If we actually fit that to the Haskell compiler, you would say, well, your data types have changed and your functions no longer fit. You get a message. And so you go, well, type signature stays the same. Also, if there's nothing in the route, that's the first equation there, then the answer is none, as before, right? There's nothing left in the route. And now on the second thing, that L thing, it's the first element of the list, right? That first element of the list, before it was just an operation, we could return it. In this case, it can be one of 2 things, which is why there's a case that finds out whether it is, well, remember, it could be either a single operation or it could be a queue time zone. And so, well, it becomes complicated at that point. We better write a helper function. Okay, so that's where we'll just defer that problem. So we'll just write, so we apply wishful thinking, very useful, and assume that there's a function called route element head. Of course, you can look ahead to the definition, which will compute the first operation to come out of a route element. And we use that here and say, well, route element of EL, it also might return none, in which case, well, you know, if you look at this thing is empty, but there's still a rest, right? So there might still be stuff in the rest, and so we just need to call this, and because there's a self-reference in the data type there, we just do a recursive call here, or if there is an operation, well, we just return that, and we're done. Does that make sense? Okay. And down here, so what's important here is we just follow the definitions of the data types, right? And if you don't let your brain get clogged up with this, you just take it an equation at a time, and then it's not particularly difficult anymore. And there's a whole school of how to teach people how to do that, which everybody can learn. So route element head here says, well, now we remember there were 2 cases, right? So there's 2 equations. One was route up, and the other one was route queue time zone. So if our route element is indeed a single operation up, we'll just return sum up. And in the other case, well, it's a queue time zone. We're not interested in the duration, which is why it has an underscore here, but it has a route inside the queue time zone. So we just need to find the first thing of that route. We've already written a function for doing that up here. We just need to call it. Does that make sense? Okay, so there's that definition. Okay, and so route advanced, remember we had that more complicated thing. I've slightly abbreviated, I think, the process of writing that. So route advanced used to have that signature in goes a route, and out comes an operation consisting of an operation, out comes an option consisting of either an operation or a route. If you think about it for a moment, well, you know that you really need to specify a time so you can keep track of how much time is left inside a queue time zone when you do that, right? And so that's what we do. And so again, we can start writing that. We can say, well, route advance of an empty list at time t is none. Route up, if there's an operation at the front, that's fine. But if there's a queue time zone, right? How do you do that, right? So the thing is, we need to represent a queue time zone, if you will, that has already been entered, right? And we can't reuse. This one just has a duration attached to it, so that's not what we want to do. So this immediately, I mean, if you go through it all the way, the compiler will remind you that there's a case missing here. So that means that you need to extend your data model. So you just follow where your model leads you and you add another case. So in this case, remember route equals route element. That's the same as before up to here. And there's just a new case that says queue time limit, and it has a time attached to it. And that time says by what time must the queue time zone be exited. At what time does it have to be done? And then again, we wrap a route inside and we turn that into a route element. Okay? And then you just sort of follow where your compiler takes you. It gets slightly longer, but the individual cases are not particularly hard. So in this case, we go, well, around advance of the empty list is none. If we have a single operation, well, then we're done. We can just split it into that first operation and the rest. And now if we enter a queue time zone, right, that is supposed to be finished within duration D, and it has an internal round RT, and after that queue time zone is that rest thing, then, well, we turn it into that route QT limit says it's a queue time zone that has been entered. So we just add the current time T to that duration, and then we record what's going on. And QT limit then just sort of needs to advance that internal route. So at that point, you don't really need to follow the detail, but I think you understand where it's going, right? You just follow, so you take an initial idea, and you just follow it through your program and through your design process where your data types take you. And that's a pretty mechanical process, but it often uncovers domain knowledge. So that means that we now have a definition for a queue time zone in progress that's built here. Now, if you
Can I ask you a question?
yeah, sure.
You defined the new advanced route thingy,
Yeah.
but by adding the route QT limit, you also had to like adjust the other one, right? Because the compiler would say there's an option missing, and then you had to. Just want to make that sure.
Yeah. So, but if you look at it now, you might play with this a little bit and write down a couple of examples, right? And here's an example. It says, right, here's a route, starts with a track in, and then there's a queue time limit, there's a queue time zone in progress. That does not work, right? That does not exist in the real world. The queue time zone, well, you enter it, and that means by definition it's at the beginning. Does that make sense, right? So now you sort of go back to your domain. And what we always try to do in functional programming is we try to make invalid states unrepresentable. It's a general design principle, right? And so if you look at this, you can now refine your data definition. You say, well, a route, it used to be this list of route elements, and that doesn't work anymore because that means that there can be a QT limit thing in the middle. And in this case, we say, well, it could either be a straightforward route, in which case there's a remainder, that's what that route rem thing means, a remainder of things that need to be done. Or there's this QT limit thing which we've lifted up from the bottom type definition to the top. And that means it has to be at the beginning, right? And if you look at the remaining type definitions, they always, so the recursion is always goes on here, right here and here, so when this thing stays at the top. Make sense? So this is now a little more complicated. And then you adjust your function definitions and things you're fine. This is pretty good. So this actually got used in the real system. Okay? But it's a straightforward process. So you do a direct correspondence of your problem domain. You try to find combinators in it that will uncover new domain knowledge, and you try to make invalid states unrepresentable. Okay. Different technique, different problem domain. Switch gears a little bit. Financial derivatives used to be big before 2008. So what's a financial derivative? I don't know if everybody's looked at that. Essentially what it is, it's a fancy contract between you and the bank maybe, and that contract specifies an algorithm, and that algorithm will take market developments as input and will give you X amount of money as a result, right? The algorithm computes that. And so it says, there's, depending on what that index does at certain times, we'll plug that into a formula and then we'll pay something out. So you might feel about this, you might not feel well about this, but there's certainly a need to model that on a computer if you work for a bank, right? And so bankers, if you ask them what's the simplest contract that exists, they say it's a zero coupon bond. So what does that mean? It just means it's an agreement to pay a certain amount of money in the future. Why is it called a zero coupon bond? Well, a bond says pay a certain amount of money at a time in the future, and zero coupon means interest, right? There's no interest inherent in this contract. And so if it says, receive 1,000 euros on July 1st, 2018, you might model this with a function called ZCB that takes in all the things that are variable in that sentence. So it takes in a date, takes in a double, which is the amount of money, and maybe a currency, and then it gives you a contract, right, between you and the bank. Okay, and here's 2 examples. So this one says, well, we have a contract that I will get on the 1st of July 100 British pounds maybe, and here's another contract that says I will get 100 euros also on July 1st. okay? And the currency might also be, doesn't have to be an actual currency, it might also be stock or something like that in financial terms. Now, I said, so another approach is not to do a direct domain model. We could just do a data type and have, because the banker person said this is the simplest contract possible, we might make that a contract constructor in a data type. But really, if we look at it, we can see that it has several parts, not just one monolithic thing, right? So it says, well, receive is what it says. It says 100, it says euros, and then there's a date, right? So maybe we could split this up. So there's a famous paper from, I'm not sure, from 2001, I think, in functional programming that says, well, we could compose contracts out of smaller parts. So we could write that ZCB function like this. It says, well, T is the time, X is how much, and K is the currency, right? And we could try to write it down like this. So we take one of that, so we'll read it from the bottom. We'll take one of that currency, right? We'll scale it up and multiply, so we'll sort of multiply it with that amount. And that amount is constant in this case, but we can imagine that there are other amounts that vary with time. So this is already a very general model. So that's what that scale says. It says take that one currency, scale it by the amount of that is specified, and when says at a certain time. So we just split it up into several, how many functions does that? 1, 2, 3, 4, 5 functions. And try to develop that into a model where there's very, very small parts, right? And again, it's a combinator library like we've seen before. So that we can use these small parts and the combinators to build larger and larger contracts out of small parts. So again, we build a data type as before. You saw the simplest a simple contract is one of a given currency, right? So I get one of a given currency right now from my contractual partner. So that's what that says, right? If there's a currency, there's a contract, that's the one contract. And this scale model is pretty involved, so this is the real thing. So this is pretty involved in that it says there's an observable of a double, and an observable is just a value that varies with time, because you might say in a contract, in 2 weeks we're going to look at something, right? The phase of the moon or something like that, or some stock index. And depending on that, we're going to give you money. We're not going to fix the amount of money now. Okay? So that's what that says. It says, well, there's an observable of a double, there's a contract, and it will scale that contract by the factor coming out of that observable and will give me another contract. And then there's when, which has an observable bool, and the idea is that you have an observable that at some point goes from false to true, right? It will switch from false to true. When it becomes true, that contract that is wrapped in here will become active, right? And we'll just write functions, and those functions just correspond to the combinators that we have up here. I'm not going to talk much about these observables or observations, but you saw that there's apparently a const observable, which is just one that is the same at all times. And there's this at thing where you can feed in a date, and it will give you an observable that switches at that time. What's important is that you have to imagine a function that, given an observable A and a date, it will tell you what the value is at that date. Okay? Everybody not still with me? Sort of? Okay, try it. So, and if you think about it, you'll realize, well, you can think of a few more combinators. So if you think of what is the simplest possible contract, right? It's not the one contract. The simplest possible contract is to do nothing, right? And so there's a zero contract at the top. Also, if you do a contract with the bank, right? The bank agrees to give you money, but it could be the other way around, right? And so you could say, well, then we're going to make that amount negative. Another way is just to say, well, I'm just going to a contract is just going to be reversed, right? That's what that give thing means, right? It means all obligations and rights from a contract are reversed between the two partners, right? A contract is always between two partners. Then you might imagine you have two contracts and you combine them in one, right? So here's an example down here is you could write and in between two contracts. Or you could say when, we already had that, or you could say conditionally, depending on some event that produces a Boolean, we could choose one or the other contract, right? So there's a lot of contracts that fired in the financial crisis that said, if certain things are underwater, then something gets liquidated. And that happened en masse, so these were conditional contracts. Okay? So you kind of, you see where it leads. Now, this is a representation of a contract as sort of an abstract entity. Of course, there's things that you want to do right? It just represents the contracts per se, but you want to do stuff with contracts. So one of the things that you want to do is you would want to determine, well, how much money am I going to get, right? Or how much money do I have to pay to my partner? So that is a pay, and at what time, right? At what time? So that thing is what's called a payout. So here it says a payout, well, it's a payout, and it carries a date, it carries an amount, that's the double, and it carries a currency. And again, we can sort of think of the same kinds of operations on payouts. So we can take a payout, we can scale it, corresponding to that scale combinator with the contracts. So if we have a payout that happens at a certain date, it says it has a certain amount A, currency K, and we multiply it, we want to scale it by that for a certain factor, then the date stays the same, the currency stays the same, and we just multiply the amount by that factor. Okay? You're all looking kind of classy. I'm trying to, so, or we could switch around a payout by just scaling by a factor of -1. Okay. So, and then we could try to define a function that says, well, again, we need sort of like with the route, right? A contract might generate many payments, and so we want to know the first, and then we want to know the rest, right? And so remember that trick that we did with the routes, where we said the rest of the route is also a route? Right? It's not some special thing. We do the same trick here, is in that if we take out that first thing out of the contract, what should remain is still a contract, right? It's still an agreement to pay certain things in the future. So we could have a step that says, well, if we feed in a contract at a certain date, it will give us a sequence of payouts that happen on that date. It will give us a residual contract, and maybe it can tell us a date when we should check next, right? Not always obvious, but we should do that. And then we just go and write that function. And remember that data type definition that said a contract is this, or this, or this, or this, or that. That guides the definition there. And again, we don't need to look at the details here, but if you just take it one equation at a time, it's not particularly hard. So if you have a zero contract, nothing happens in the future. There's no obvious date to check for. If there's one currency, if it's 1K, so 1 unit of a certain currency, that will pay out today, 1 unit of that currency, and what remains is nothing, right? If you have give, a contract where everything is reversed, well, what do? Is we step that contract that's inside, and we take all the payouts, P, and we map. And map, do you know how that works? Okay, so map, apply a function to every single element of a list. So we just map this invert function that we wrote that reverses all the amounts to that, and then we take the remainder here. Scale is sort of, scale, we need to call that function that we assume to find out what the value of that observable is, and use that pscale function to scale all the amounts. So you really don't need to look at all the details here. If you have an AND contract, you need to step both contracts and sort of recombine what remains. So again, if you just think a little bit of what the parts mean, then it's not particularly hard. So that means you now have a definition of contracts. This is not, if you're interested in that, this is sort of the, I've been thinking about that, this is the opposite of domain-driven design, because there's no boundary to the context, right? This is a general definition of contracts that can be used in many contexts. So if you're a bank, there's many different departments that deal with the same contract. There's the front office, the middle office, the back office, and they will all interpret the contract in different ways. And so typically this is going to be the back office that wants to know what the payments are. And the front office might be interested in the value of that contract, so it might write a different function. But again, the function operates on the same representation of contracts. So,
but depending on like which department is dealing with that, the contract is more than that. It's like there might be some metadata which is relevant for one part of the company and for the other part not, or would you wrap the contract in something that has a contract and the metadata? Or?
No, good question. So no, this contains everything, right? This contains the abstract idea of that contract, right? And it can be interpreted in different ways. And this is very different from how a lot of banks, well, it's been a while since I actually dealt with this stuff at customers. And there it was just the bane of our lives that everybody had their own representation of contracts, right? And of course in the bank, well, your business, depending on how you look at it, you might think that your business depends in some sense on them being consistent. This is complicated enough that that does not happen in practice, right? So there's real value in having a single coherent representation with a defined semantics that can be interpreted in different ways and where consistency can be checked, right? And so there's an entire company that's founded on that idea, Lexify in France, that has built a product that's used substantially in banks. Okay, so we've seen that. So first we said one-to-one modeling, right? We've developed that into combinators. So combinators is a constant theme in functional programs. And then another approach is that we take our understanding of the domain and we try to smash it into very, very, very small pieces, and then introduce combinators to make those small pieces into bigger things and bigger things and bigger things and bigger things. And the great advantage in that is that we can write functions like that step function that only has to be defined on the small things. That's usually easy, and we don't have to deal with the complexity of the domain that is inherent in a direct model. Okay. So here comes the hard part now. It's about algebra, so something from math in school. So a friend of mine, Brett Jorge, thought about a popular, so he wanted to draw diagrams, and he wasn't good at drawing, so he wanted to write computer programs that draw diagrams. So he was thinking, well, what's a diagram? And he said, well, we can think of primitive diagrams like a square or a circle, and we can think of combining them. So we can put two diagrams together, right? And we can put them side by side, and that thing, two diagrams side by side, because we deal with combinators, they will also be a diagram. Okay, so that's the easy part. So then we can take two diagrams where we've put things side by side, we can put them on top of each other, and again, that will be a diagram. If you think about this, it might look like this. So there's a data type for diagrams. We don't exactly know what it is, but there's two functions for squares and circles. And we feed in some size parameter, here double, and a color, and we will get a diagram. Okay? And we're not going to worry about how those primitive things are represented. And then we imagine that we have two combinators beside and below, and they will take two diagrams and produce a bigger diagram. Okay? And that's been how we've been doing diagrams for, 30 years in functional programming. In Haskell, people often use like symbolic names for things, right? Sometimes to their detriment. So in this case, they say, well, for combining two diagrams, we could also have this general idea of a binary operator, right? And here's a binary operator. It says it takes an A, it takes another A, produces an A. And these combinators occur in many contexts, right? Whatever. You take a shopping basket, you could merge it with another one, and you could again, whatever, right? So whenever you see this, whenever you have a binary combinator that has this kind of type signature, so you might remember in math class in school, there were some laws, right? And so in particular, there was this law. Does anybody remember what that was?
Associativity?
Associativity, very good. Excellent. So there's always that one person in the room who remembers what it is, right? So right, when you have this kind of combinator, you can think about whether it's okay to shift sort of parentheses and nest it. So what that really means is that things are sort of arranged in a sequence. And so when you have a combinator, it's always good if it's associative, because it allows you to reason about how it behaves, and it behaves in a regular fashion, right? And a lot of binary operators are associative. And so, I kind of gave that away. So what's the structure? So when you have associativity, what's that called? Well, it's called a semigroup in fancy mathematics, right? And so often people complain about the fancy names used in functional programming. I can't help you there, but in math, they have names for this, and therefore you could also give it a name. In Haskell, it says a semigroup A is, well, it's some A, some data type A, and it has a binary operation, and it has this associativity law that holds. So you can write that down. And so sometimes what you also have is you have what's called a neutral element, in that you have this binary operation, and when you combine something with that neutral element, the same thing will come out. So typical example is you add 0, right? Same thing comes out, or you multiply by 1. Right? That's the neutral element with respect to multiplication or addition, respectively. Okay? So when you have that, here we can call it epsilon. So when you have this thing, so if you combine d with epsilon or d with epsilon in one of two ways, you will always get back d. And This is called a monoid, right? And this is also pretty common. So most semi-groups that you find out in the wild, they're also monoids, right? You go, oh no, right? But try it at the next whatever office party. It's a monoid, and then maybe it will be the star. So you've got to think when you have this, so this epsilon thing, it has to be like the simplest thing that you can possibly imagine, right? So it has to be, when you're thinking about numbers in addition, you think, oh, 0 is the simplest thing. But we were thinking, so you can imagine that this, if you put two diagrams beside each other, that's also an associative operation. So diagrams form a semigroup, right? Does that make sense? Right? So that sounds much better, right? Diagrams form a semigroup. They have an associative operation. Yeah, look. Are shopping carts associative? That got you thinking. I tell you, maybe they should be, right?
Maybe they're not.
Maybe they're not, but maybe they should be if they're not, right? So that's another way of thinking that you could use, right? If you see a binary operation and it doesn't have the laws that a lot of others have, then it makes sense to think about whether they should, and maybe it has positive consequences to if they do. So you got to think what's like the simplest diagram. In particular, it's the diagram that if you put the diagram beside any other diagram, the same diagram comes out. So this is the simplest diagram. So, right, that's it. Okay. So anyway, but you think, so this is the way that the functional programmers have been doing diagrams for ages, literally for decades, right? Brett was thinking, but I want to rotate diagrams, right? I want to rotate. And then he was thinking, well, this rotation thing, it plays havoc. It does not play nice with beside and below, which are inherently horizontal and vertical, right? So you can't imagine, so you can construct it in this way, in that you first put things beside each other and below each other, and then you rotate, but you can't do it the other way around, right? And that bothered him, right? There were not enough laws that held. And so he thought, well, a one-true combinator should not be beside or below. It should really be something that just puts diagrams on top of each other, right? He played with that idea. Not because it was the most intuitive idea, but because it gave him better algebraic properties, more algebraic properties. So he's trying to run with that. And so then there's this problem. And that means that you also want to be able to put those two things next to each other, even though it's not vertical or it's horizontal. In an diagram, you want to be able to put things next to each other in any direction, right? And so you're thinking, how am I going to do that, right? And you figure the way to do that. So maybe if you're familiar with a lot of ways of doing geometry, what you usually do is you put a bounding box around things to arrange them, right? That bounding box, it doesn't rotate. It has to be a rectangle usually, right? And it has this problem. But what if you have a shape like an ellipse, where if you just put a rectangular bounding box around, you want to put something right here on the ellipse, right? The bounding box is going. So what you do is you do an envelope. You specify a vector, and you then give how much you need to stretch the vector in order to have the perpendicular line that is just outside your shape. Right? That's an envelope. Right? And so, and that means, that's great, because that means you can really compose pictures with the help of those envelopes by just shifting them by that amount, by just using them this way. Okay, does that make sense? Okay, and that means I can't just put them beside or below. I can put them next to each other in any direction I want, just by shooting off an arrow in that direction and then using the envelope to figure out by how much I need to shift that out.
Okay, and the third diagram happens to be just because I'm not allowed to turn the square anyway.
Okay, you could also rotate the square, but then you need to, so good point, right? Yeah, good point.
I'm not allowed to rotate.
Yeah. So this example just shows you how you can arrange in different directions, but it doesn't really show you how the rotational thing works. So you can think about how to compose. So again, so when you do this, you have a shape and you have an envelope, and remember the shape had this monoid operation where you can put two things on top of each other. We can think about what does that do to the envelopes, right? And it does something very simple to the envelope. It might be complicated, but it's actually fairly simple, is in that you always take the maximum envelope, right? And that will get you where you want to be. So what the Haskell programmers, so this is mainly a story about what Haskell programmers do, they have more practice with this, is they think about these diagrams in terms of semigroups and monoids. And so they write down semigroup and monoid in their definitions. Right? And so they say, well, a diagram is just a list of primitive shapes like squares and circles and things like that. So that's the actual definition from Brent's very fancy diagrams package. And then it says, well, a list of things, right? A list of A's is always a semigroup, right? And I can always combine two lists by concatenating them. And this is also an associative operation, and it also has, well, it's also a monoid, where we can just take the empty list, right? And here it says, well, and a diagram is a semigroup, and we explain that two diagrams are combined by just combining the lists of the primitive shapes in reverse order, right? He had this idea that he gets more algebra if we do it in reverse order. And also a diagram is a monoid, and we just take the diagram of the empty list, which is that picture that you saw where you saw nothing, right? So don't worry, this is the last example. We'll get through that. So, and he just took that idea and he thought, well, an envelope, first of all, so what we want really in an envelope, as I said, is we shoot an arrow, we take a vector in any direction, and it will just give us the factor by which we need to stretch that vector so that the perpendicular line is just outside the shape. And so that means we get a function from V2, which is a vector in 2 dimensions, to a double. Okay, that's what constitutes an envelope. And then goes, oh yeah, we're going to do homomorphism. So, well, he just tried to apply algebra to this, right? Homomorphism sounds really nice. And try to make things fit in an algebraic framework. And said, and so remember, we need to, if we're going to combine two pictures, we also need to be able to combine their envelopes for this to work out, right? And so it turns out that if you apply enough algebra, you can just, you can write very simple definitions here. So in this case, it says, well, so in this case he says, well, we're first going to define how, if B is a semigroup, we can explain that functions from A to B are also semigroups, right? And that we say, well, if we have two functions, f1 and f2, and we combine them, then out comes another function, takes an x, and we apply f1 to x, we apply f2 to x, and now we're in the semigroup and we combine the two results, right? And so, you know, suddenly you see algebra everywhere. I mean, Brent certainly is somebody who sees algebra everywhere and just tries to run with it. And once you write down a bunch of stuff like this, then it becomes very simple to write it down for envelopes. But you also realize more domain knowledge, as we saw earlier. So in particular, you need to realize, well, the empty picture doesn't have a natural envelope, right? And also, what we want is we really, so what we want is we want a structure where we can represent a maximum also. And so here's that question: what's the envelope for an empty diagram? So well, let me backtrack a little bit and explain that why it says maximal there. So the question is how. So we want to use sort of the semigroup and monoid properties on the small things, right, to explain the semigroup and monoid properties of the larger things. Particularly, we want to use semigroup and monoid on double to explain how it works on envelopes. And remember, we used the maximum to explain it on envelopes, right? But if we just have two numbers, there's various different ways to combine them that form monoids, right? We could add two numbers, we could multiply them, or we could form the maximum, which is what we want, which also forms a monoid, right? And so what we do is we just write maximal in here, and there's a data type, and it says, well, a maximal is a semigroup and a monoid in these ways. And also we need this option thing that says it's there or it's not to explain that there's no envelope for the empty picture. So it's a special case. So you just take it and run with it, and then it all works out very nicely. And it has this beautiful diagrams picture package that you can use to draw diagrams systematically with programs that comes out, right? Just by really insisting on having a lot of algebraic structure in what he does, right? And that might seem very fancy and theoretical to you, but once you get used to it, you see it in a lot of different places. Maybe I got you thinking about shopping carts already, and it becomes tremendously useful. So to give you one example is in that semiconductor domain that you saw at the beginning, one problem is that machines break down all the time. And so if you write a scheduling system for this, you have to hope that that things work all right. And if you have a computer system that deals with that, you have to manage that hope. And so we were thinking, what is hope? And so we found out hope are an algebraic structure called a monad. And once we realized that, it got, I mean, we were able to throw out, 75% of the code. It got really simple, and things worked out very nicely. So there's real value in understanding. I mean, there's maybe a half dozen of these algebraic structures that are useful in a lot of domains. So you don't need to know that many. I mean, there's a lot more that are slightly less useful, but still useful. So let me reiterate. So in functional programming, when we do design, first thing that you do is you try to do a direct correspondence between your code and your domain. And that's right in line, of course, with domain-driven design. When you do that, you try to find combinators. So rather than having hierarchical models where you assemble things into different kinds of things and different kinds of things, you always go up and at some point you've reached the top. You try to find combinators where you try to build larger things out of smaller things, even larger things. You can do that infinitely or arbitrarily anyway. And even though you don't always see immediately that there's recursion in your problem domain, it's often very useful, and we almost always find something like that. Another technique that you can apply if you think that your problem domain, if that direct model is somehow too complicated, is you smash it into very, very small bits, right? And you then try to combine your more complex bits out of smaller bits. And write it down as a data type definition, and then write semantics functions on it. And what we saw is it's very useful. Well, maybe you didn't see it, but one of these days you'll see it. That it's very useful to think of your domain entities in terms of algebraic properties. So I often see, once a month I see a snide comment on Twitter, and it says, monad is not part of your domain vocabulary. Of course it's not, or monoid or something like that. It's a property of things in your domain vocabulary, and knowing that is tremendously useful. And so, and throughout what we've done is we've used abstraction. So there's a picture called abstraction there, and functional programming is very good at that. So that's just a common theme throughout everything that we do. Okay, you made it. Anybody have a question?
Yes.
Yeah.
How do you test these kind of data structures?
So the great thing is these are all functions, right? Yeah. And so that means their output is solely determined by the inputs. And so first of all, you can just write we just often write unit tests the way that you know them. But with the exceptions that there's basically never like a setup or tear down thing, right? That's kind of rare. That leads into a larger issue of sort of architecture of functional programs, but the meat of your domain functionality should be written in this case. So that means it's very nicely suited towards unit tests. Now you saw me talk about algebra, right? And so you would like to verify that your thing that you build is indeed a monoid, right? So that's great because you can write that monoid property as a function also, right? That returns true or false, right? And functional programming has produced a very nice technique called quick check, which will automatically generate a lot of test cases from that also has been imported into object-oriented languages. And so, moreover, John Hughes, the guy who invented quick check, then said, well, maybe we can use, since quick check can verify whether my thing is a monoid or not, I can add another layer on that will discover what things it is, right? By just testing for them. And so there's another thing on top that he has that will do that. I would like to extend your question. It's not just a question of, depending on how high your requirements are for reliability, you might not be, testing might not be sufficient, even testing with quick check. And then you might want to prove certain properties of your program. And since, well, you saw that correspondence between algebra and functional programs, you can use algebra to make proofs if you want. If that makes you happy. It makes you pretty happy. Yeah. Well, I mean, you don't want to do that for your entire program. Well, you know, if your employer pays for it, maybe you enjoy doing that. But sometimes, right? Especially if you're writing things like distributed systems, or you do event sourcing, or something like that, right? Then you really need some properties to hold, right? And if they don't hold, it might blow your entire, data out of the water because you stored it in the wrong way, and you might discover it too late because there's a lot there. I mean, I don't know, right? But event sourcing also often has subtleties, and so you want algebraic properties like associativity, maybe like commutativity, or things like ivity at the end. And so some basic things you might want to prove, right? And so this is eminently amenable to that.
If you have to deal with mutable state,
Yeah.
like what's the strategy like? Put it aside somewhere where you can test it and get your domain model like free from that, or how to deal with it? Because all your examples were like, yeah, that's pure functional.
These are pure functions, yeah.
Sometimes there is a database.
Sometimes
There's a database.
So first of all, so the question has different layers, right?
Yeah.
So one of them is in general. I mean, of course, at some point you want to mutate the world around you, right?
Yeah.
So your program as a whole is supposed to have an effect, right? And so what you strive for, you don't always succeed, but in functional architecture, is that you push the side effects that mutate the world to the edges of your system, right? You do pure computation in the middle. And that's an approach that works reasonably well. Still, functional programming encourages you to push that boundary, right? So whenever you have a database, right? So functional programming sort of wants you to do that database in an append-only fashion, right? And to not delete things or mutate things in place. And once you do that, so that leads into sort of event sourcing approaches, but you don't need to get that fancy about it. But that often has very beneficial side effects, right? And you can then think, well, I have an append-only database. It grows and grows and grows and grows. Maybe it's going to grow without. What am I going to do, right? But then you think, well, maybe that really old data, it got superseded by subsequent data, and if I leave it out, I won't change the semantics. If only there was some algebraic property that explained how that works, right? And then you go, and then you're cooking, right?
Okay.
Does that make sense?
Yeah.
One more question. You're gonna have one more. So we have three. Oh, I see a couple people are going. You have a question?
No?
No?
I'm just inspired.
Which one is your favorite functional language?
So I don't have one. I think I'm too old to play favorites here. I do see that the Haskell programmers seem the happiest. So I'll tell you that. Right?
How do you measure that?
Huh? I have smiles on their face. No, there's actually, I saw statistics, somebody did like the programming language ranking something on weekends, right? And Haskell is on top.
It's maybe because they can't use it at work.
Yeah, well, obviously they want to use it, right?
Yeah.
So that's just my subjective impression.